because I've been interested in two different areas, and since I retired, one of them has been the Big Bang, or the fact that I don't leave the Big Bang. I've got my own model called the Big Wave, which actually explains the universe as having a center and moving in space from that center and not space expanding. Anyway, that is a subject for a different time. But part of the whole question of the Big Bang is whether general relativity is correct and has anything to say about the way the universe operates. And it appears that the only two proofs of general relativity, experimental proofs, one is the anomalous precession of Mercury's orbit, which was from a 1915 paper by Einstein, and the other was the 1919 eclipse, which presumably showed the bending of light. I've been told that there's a third experimental proof, but I don't exactly know which one it is. But any major theory that has so little experimental proof has got to be suspect as being unconfirmed. So what have I done here, and with whom? It turns out I've been working with a Russian by the name of Anatoly Vankov, who used to work at the Obninsk laboratory, which is just southern border of Moscow. But he's now living in Rhode Island somewhere, and he's been in the States for some period of time. We started to discuss things, and he does not know German. And so somehow or other, he got me to translate Einstein's 1915 paper on Mercury and Karl Schwarzschild's 1915 letter to Einstein on Mercury, telling Einstein that he was making a big mistake and had all sorts of problems. I also ended up translating from the French the Rydin Leverrier's 1859 paper on Mercury, so I know what the actual data is and what they thought they knew about Mercury. So I'll go from the back to recent history, and then I will end up with some of the things I've been doing with Anatoly. He did not want to be a co-author, although I offered. I told him I thought we should have both our names on it. He said, go ahead and present it, because he's working on a couple of papers and he's going to publish. Where did Mercury strange movement come about? Well, it's written up in an 1859 paper, which is approximately 200 pages. I translated a little bit over 100 pages just to find out what he did. And I will present more or less what he's done. But basically, they do a lot of fitting with periodic functions, time-dependent functions, and a few other things to about 100 years worth of experimental data, and then attempt to use those fits to project further on. And Leverrier became famous for doing exactly this and discovering Uranus or something of that nature due to a perturbation in the movement of other planets. That's why he got very interested in this thing. So he actually wrote a first paper in 1841 and then corrected it in 1859 and got 39 arcseconds per century advance in other words, you've got an ellipse that's slowly turning. And the data was reanalyzed in 1895 by Simon Newcomb, and he pretty much used exactly the same procedures. And of course, they didn't have computers, so it's not surprising that he got pretty much the same thing. He changed the number from 39 to 43. Einstein did a theoretical paper, got 43, said the experimental data at that time was 45, but he said that he has just proven that general relativity is valid. Clemence in 47 affirmed 43, but of course that was still before computers. I started using the first computers in the 50s sometime, so they were still doing hand calculations. And surprisingly enough, now that they can do numerical calculations to all the planets, they have a built-in general relativity correction that they can't disable. So you aren't going to ever find a discrepancy if you built it in before you start fitting. Now, there were critics over the years. Charles Lane Poor in 1924 said this is a very small discrepancy. I'll show you how small. Impossible to resolve. Rana went through the data in 87 and found a whole bunch of errors. Inouye did it, some work in 93 and found some more errors, and you can throw out some data and you get better fits and so on. And I got interested in the idea of what is the experimental support for general relativity, and concluded that you really shouldn't be dealing with general relativity anyway. I think I gave a paper in Tulsa or someplace on this. And Vankoff wrote one paper where he basically found an error in the Einstein calculation, and then the new paper does the whole problem numerically and shows how bad the error is. Those are some of the things I'm going to show you. But anyway, what do we do? Well, we sit here on Earth and we point our telescope, and of the movement of 5,600, 5,000 of it is just due to the fact that we're moving. So we have to correct for 90% of the value is just the fact that we're on an unstable and moving place taking our data. They have calculated that the tugs of the other planets is about 530. I'd like to point out that this isn't a continuous 530. You get a lot more attraction when Jupiter is aligned with Mars, and when the two planets are close to each other, and when they're far away, you get little. So it's not a nice linear progression under any circumstance. And this shows that they built in general relativity as 42.98 plus or minus 0.04, like it's the most accurate thing in the entire table. And of course, that's impossible. So the total movement is large. The other planets is about 9 or 10%. General relativity is less than 1%. And none of these values have changed for years and years and years. But Leverrier discovered Neptune by effect on Uranus. He did all these mathematical fittings by hand, using tables no less. And you can make errors just in interpolating in tables, one in the wrong column. He made his orbit corrections for other planets, and he thought that he had discovered Vulcan somewhere near Mercury, and unfortunately they never found Vulcan except in Star Trek. But the fits did change over the years, but not enough to change any of their conclusions, because they were using the same methodology. I tried putting in modern masses, and some of the masses of the planets were off by 5 and 6%. Didn't have any effect at all in the fits. So that's one of the things that happens with fits. They're self-correcting. Newcomb didn't do anything different. Now Einstein, in his 1915 paper, he expanded general relativity to low orders of Newtonian gravity, and he came up with a correction to a pure elliptical orbit by adding a cubic term to an otherwise quadratic expression. And he got a correction to a pure elliptical orbit, and he stated that that proves that general relativity is correct. In that same paper, the paper itself is rather disjointed. It starts out with the general tensor equations of general relativity, and then in the second section, he suddenly makes a correction to the bending of light and doubles its previous amount of light bending, because I guess the first time it was equal to Newtonian light bending, so you had to have it somewhat different. And so that set up the 1919 eclipse, which was also pretty much falsified by somebody who should have known better. Schwarzschild sent Einstein a letter, two-page letter, which I also translated. Both of these, the 1915 paper and the letter, are on the web, as well as my translation of Leverrier's paper, so you can see for yourself. But Schwarzschild said, I went through your equations, and I found something else than what you showed. You left out a term, and if you put that term in, the problem is physically undetermined. I kind of think of that as like if you add an odd term, sometimes that doesn't give you a contribution. You only get something from even terms. But anyway, Schwarzschild not only disagreed with Einstein, but then he made his own solution, and he published it in 1916. And his solution does not have a singularity. He, in fact, prohibits a singularity from existing in the Schwarzschild solution. And what's his name from Australia? Crothers, yeah. I've written a paper with him, and Crothers shows that there is no singularity, and you can't have one. And Crothers also argues that if you had a singularity, then you wouldn't have mass included, and you wouldn't conserve momentum, and a whole bunch of other things. So, but anyway, what does it come out to be? Well, Schwarzschild continued. He said that your solution is going to be divergent, and that's the clear meaning of the problem. And we've had a friendly war, which allowed me to stroll in your ideal land or your fantasy land. But unfortunately, Schwarzschild was killed the next year in the First World War, so he never had a chance to defend any of the things that he did do, unfortunately. Charles Lane Poor basically said you can't disentangle the motion the way you're doing it. It's not a linear problem, it's a nonlinear problem, so how can you put together a bunch of linear terms and get answers? And how can you distort time, and how can you distort distance, and so on. Clemence in '47 admitted that observations of Mercury are among the most difficult in astronomy. Its path is not an ellipse. Determination of the motion is the most difficult problem in positional astronomy, and still they persist in giving answers with accuracy of a couple of percent. It's unbelievable that you can take the most difficult problem in positional astronomy and get that kind of accuracy. Rana had his, well, I don't need to go through all the details. Low degree of precision. I came at it from a different standpoint. Bob Heaston, who used to come to these meetings but unfortunately passed away, did an analysis of Einstein's paper, original 1905 paper, I guess, and it took him 10 years to go through the derivation and pointed out all sorts of problems. But Heaston said you basically should not have gotten the singularity. The singularity came in when you set C equals, I'm sorry, this is the general relativity paper. And Crothers So what he did was he set a tensor to 0, but that leaves the mass out, and there's no singularity. Schwarzschild shows it in the singularity. Van Hoff pointed out that there is a numerical solution, but they stick in this general relativity correction, so you can't possibly tell the difference between experiment and theory. So what I took away from Van Hoff that really impressed me was that the numerical solution that they got, regardless of whether it was right or not, is tortuous. And show you what that means. This is a numerical solution over some period of time. Does that look like a linear progression over any period of time? Seems to go up, seems to go back down, wiggles around. That's because none of the planets are ever in exactly the same position at the same time, so they don't interfere with each other in the same way ever. And so how you can believe that you're going to come up with a discrepancy of less than 1% when the data you're using is of this nature is beyond me. Anyway, Van Hoff did a mathematical paper that I worked with him on, and he showed how Einstein took the cubic term out of the denominator to get the correction, and how he got his answer. But it turns out that if you do it right, the net correction is 0, in agreement with what Schwarzschild tried to tell Einstein. You're going to have trouble reading this. So I'm just more or less going to show what you have is a differential equation, which ordinarily is a quadratic expression, and Einstein added a cubic term with a known coefficient. And then he proceeded to pull out that alpha type term and come up with a correction for the orbit. And what happens is you get an expression like this with an elliptic integral, and the original elliptic integral is just the quadratic term in the square root in the denominator, and alpha 1 and alpha 2 are the roots of the quadratic equation. What Einstein said is, well, if I tack in that extra term, it doesn't really change the solution of the two major roots, so I'll leave alpha 1 and alpha 2 alone. And then I will assume that the original orbit is still correctly in there, so I just have to calculate the correction term. And that's what he did, was to calculate just the correction term. And I went through his mathematics, and he in fact did pull out the correction term properly. He reduced it down to the original elliptic integral times some other terms, and the extra term he put in, alpha, is in there, and then you can integrate it, and he in fact got the right answer, and evaluated it properly and came up with his I did that wrong. Finally came up with his 43 arc seconds per century, while the astronomers give 45 plus or minus 5, and he said that this is proven that general relativity is correct, and whatever else he claimed. It made him famous. But now Van Hoff said, well, this is what you should have done. When you have a cubic equation, you have a characteristic equation that couples all the solutions. And so what you really do is you break the problem into two pieces. And this is what you should get. There's your characteristic equation, which couples the three roots to the constant alpha. And when you take that expression and expand it out, you get two terms. And the first term looks pretty much like the original orbit term, and the second is the correction. Now the problem is that you have to figure out what the limits are. And I slipped one. Well, I'll just keep going. In effect, what happens is if you fix the limits according to the slight change in the solution due to the third extra term, and you do the first integral with properly, what you get is pi minus 3/2 pi alpha. And Einstein's correction was plus 3 pi alpha over 2. And if you add the two terms together, you get pi, which means there's no correction at all. So I believe that Van Hoff has proven that, in fact, this mathematical procedure was just so much arm waving and did not come up with a real answer. But now Van Hoff recently decided to take that differential equation with the alpha in it and just numerically calculate orbits. So I can put together a numerical method, and I will, for a given mass, I'll just start the orbit out and see where it goes. And here are a couple of his solutions for more or less planet-sized bodies. One is a slightly expanding orbit, and another is a slightly contracting orbit. But what you notice is the numerical solution is not symmetric around the origin. In fact, what do you call this when the curve starts wandering? That's what it's doing. And he calculated how much it changes over different parts of the circle, and you find out it's not changing uniformly at all. So if you use this correction in a real orbit calculation, you get a ridiculous orbit. Finally, he said, okay, what happens if I go to a very heavy, not just a planet, but a very, very heavy body? And what happens, two things happen. One, you have an orbit that collapses towards the origin, but it never gets there. And the second thing that happens is that somewhere in the process it exceeds the speed of light. Of course, there's no correction to keep the speed from going faster than the speed of light. But regardless of that, what you get by trying to use Einstein's correction directly is nonsense. So the final conclusion is you simply can't get a correction for Mercury out of Einstein's equations, period. They were improperly calculated to begin with, and just using Einstein's methodology gives you ridiculous answers. And I think that's the end of this. So I think that the perihelion change of Mercury is probably statistically insignificant, that the less than 1% apparent motion could be zero, probably is zero. The actual path is tortuous at best. It's not any kind of a uniform advance. Einstein didn't do the whole solution. His correction vanishes if you do it right. The numerical solution gives you where those orbits. And so I think that means that all black hole physics is nonsense. Black holes aren't singularities, and we can't say what's going on in them or near them anyway. And that pretty much ends the talk.